All right, let's get started. So this week is all about graphs. We're going to do graphs and breadth first search. And this is going to be our last concept that we cover in 116. This will round out all of our topics that we need to know. And then when we come back from break, it's review, examples, all that kind of stuff. So our goal here in terms of the homework is to get our AI to be a little bit smarter. So through tasks 1 and 2, you have AI that will hunt down the closest player if it's close enough. And then once it gets even closer, it'll start firing at that player. And the AI will hunt down other AI. If they spawn in 2 adjacent spawners, they'll go towards each other and they'll both shoot at each other. But they'll get stuck on walls. If there's the AI player and another player on the other side of a wall, there's a wall right in between them, they'll just walk up against the wall and not be very smart about that. Our goal for task 3 and the application objective is to get these AI to avoid those walls, especially the application objective. Task 3 builds into the application objective, which finally gets those AI avoiding the walls and going around walls and not getting stuck on them to be able to hunt down players. And that's what we want from our AI. We want them to be a little bit intelligent. So we're going to need graphs. We're going to need breadth first search. We're going to use breadth first search to perform this pathfinding task. That's our goal for the week. Today and Wednesday, I'll cover all the concepts, all the new stuff that you need to see to get that done. So by Wednesday, in 2 days, you'll have everything you need to complete all the way through the application objective of the last homework, all of the homework stuff, and all the quiz and interview stuff also. And then on Friday, we'll do some examples. I'll do mostly spoiling test cases on Friday, which I've been pretty consistent about this semester, where every Friday is, not every Friday, but every relevant Friday where we cover new content for a task, that I would do the testing, spoil some test cases on that Friday. One obvious exception, last week I didn't do any. On the last lecture on Friday, I didn't do any because there's no testing required for task 2. So really nothing for me to spoil. But on Friday, we'll spoil some test cases for test 3. So any questions before we get into graphs? All right, let's get into graphs. So we know some data structures so far. These first 3 you've been working with ever since you've heard the term data structure in 115 is a sequential data structure and a key value store. And our sequential data structures are arrays and linked lists. You've used linked lists before 116, before 2 weeks ago when we learned the structure of a linked list. You just never had to care that it was a linked list. It was just some sequential data structure. And you would access values by indices, not knowing that, oh, it's a linked list, so that's actually inefficient. You really didn't have to care until 2 weeks ago when we learned the structure of a linked list. And then in 250, they'll really hammer that home, the difference between arrays and linked lists. But you've used them before 116, and you probably didn't know or care which one you were using, either an array or a linked list. As long as you could access values by indices and add things to them, it didn't matter to you. Whether it's an array with a wrapper class around it that's simulating you being able to add elements to it, or a linked list that just adds elements and is inefficient when you're looking up elements. It didn't matter. It will very much so in 250, and a little bit so in this semester. And then key value stores, you don't want just a sequence of elements, so you're not concerned with elements just in some particular order. And with key value stores, you wanted to store values at specific keys to be able to represent your information in a slightly different way. You want to associate this associated data structure, associate keys with their values instead of just saying, here's a sequence of things in some particular order. So it gave us a different way of representing things. And then finally, last week, introduced a new data structure, a tree, which gives us a way to represent information with a completely different structure. This idea of a branching data structure where instead of having a reference to one node or a sequence where you just have the next node whether it be an array or a linked list. There's the next node, the next element, the next element. Now we have a way to have branching where each node contains its value and references to 2 elements. And that step from 1 to 2 is such a huge step. It's a completely different data structure that lets us represent data that we couldn't represent before. Like a binary search tree, we can't build that with an array or a list. It would just be a sorted array or a sorted list, and it doesn't give us the efficiency that we want out of a binary search tree. That log n insert, log n delete, and log n find. We don't get those with arrays or linked lists. So with these 4 data structures that we know, how are we going to represent data like this? We have either subway stations with lines connecting them. We have intersections, road intersections, connected by roads. Or we have the example that we're going to use throughout this and Wednesday's lecture, this early days of the internet, before it was the internet, of having routers connected to each other through cables. How are we going to represent information like this in the existing data structures? This is going to be a bit of a challenge. So let's try a few things. And like I said, we'll use this example throughout the slides. Let's start with our tree. Our tree kind of seems like the data structure that's going to work the best for this. We definitely have some branching structure here. This isn't just a list or a sequence of nodes. Key value pairs don't quite make sense, but trees sound promising. And specifically trees, not binary trees, because we're going to need more than 2 children for each node. And let's just build a tree like this. Let's start with UCLA as the root node. And we're going to say any nodes, any routers adjacent to this one, we're going to say are the children, the child nodes of this node. So UCLA is connected to Stanford, SRI, UCSB, and RAND. So we'll have those be child nodes of this root node. And we're going to do this for each node. So we'll visit Stanford. Stanford is connected to SRI and UCLA. And we immediately run across a pretty big issue that needs to be resolved. So Stanford is going to have child nodes of UCLA and SRI, both of which are already in the tree. And we're also going to have this infinite structure here where UCLA has a child of Stanford, which has a child of UCLA, which has a child of Stanford, which has a child of UCLA. It's going to go on forever if we go this approach. So we need something else here. And maybe the idea is, okay, instead of having references, instead of having UCLA, we'll have references to all these nodes. And when we visit Stanford's child nodes, instead of creating new nodes for them, we'll store references to the existing nodes. Stanford as child nodes will have references to this SRI and this UCLA to avoid the duplicates. But then what happens when we run our traversals on that tree? We run a traversal. UCLA makes a recursive call to Stanford, makes a recursive call to SRI and UCLA, which makes recursive calls to Stanford and SRI. We're going to go infinite with our traversals as well. So we have a few issues that are going to come up due to the fact that we're going to end up having cycles in our tree. Our tree data structure can't have any cycles in it, so no child node could have a reference to one of its ancestor nodes, its parent or ancestor nodes in the tree, because we'd go infinite. We'd have a cycle, which means you just run in loops in the data structure. Not allowed in a tree. So let's try this again. We're going to kind of do what I said, where we're going to just reference the existing nodes, except we're going to represent our information in a different way, which of course, as the topic of the whole week implies, this is going to end up being a graph. So we're going to just have links to the existing nodes and not add the duplicates, but we do get these cycles. So since we have these cycles, this is no longer a tree, and our tree algorithms are not going to work, or algorithm, I guess singular, but we did our 3 traversals. I guess that's plural. We did 3 of them. Our traversals and our binary search trees don't work at all in a structure like this when we can have cycles. Having a cycle in a binary search tree doesn't make sense. Just doesn't make sense. Yeah, everything in the left node is less than, right node is, or right subtree is greater than. But if that subtree contains that node itself, if both subtrees also contain that node in a cycle, it just doesn't make sense. So all those get thrown out. So we're going to have these cycles, which really changes the way that this structure works. Graphs are going to work in completely different ways than trees, and completely different ways than linked lists. We can't use any of those algorithms anymore, any of those ideas. So we do have a brand new structure here. We don't want that infinite recursion. We don't want infinite nodes. We don't want infinite recursion. So we have to avoid all of these things when we're working with graphs. And to do that, it will be a whole new idea of a structure. Like linked lists, it was nodes, and it worked on references to other nodes, and that linked the nodes to create the linked list. With trees, we did the same exact thing, except we just did 2 references. The structure, the fundamental structure, was the same exact idea. We just had 2 references instead of 1. That's not going to be true with graphs. With graphs, we're going to store these in a very different way. We're not going to mess with references at all. We're going to have just one big old data structure with all of our information. And that information is going to be nodes and edges. So nodes, we're familiar with the idea of a node, where each one of these values is going to have its own node, but it's only going to know its value. And then any connections between node are going to be stored separately as edges. We're storing this as nodes and edges instead of nodes with references to other nodes. So node, kind of like linked list and tree, except no references, just stores the value. An edge connecting 2 nodes. Those are 2 things that we want to store. The 2 things we want to store in our data structure, nodes and edges, to represent a graph. We're actually going to build graphs by combining the existing data structures that we know. We're going to combine them in a way to build like a more complex data structure of a graph. This is how we're going to do that, with an adjacency list. Now, I just assumed this in the other lecture, but everyone looked a little confused, so I better ask this time. You've been doing graphs in 191, right?
Yeah.
Okay, good. So those of you in 191, you've seen ways, so far this has all been review. Those of you not in 191, I want to make sure I cover everything in case you haven't seen this stuff before. But you've seen 2 ways to represent graphs in 191 if you're in there. Adjacency matrix and adjacency list. In 116, I'm going to stick just with adjacency list. We're not going to talk about adjacency matrix at all, except just when I go off script a little like I'm about to do. Adjacency matrix is going to store all of the edges between nodes by being a matrix of nodes to nodes. The rows are columns, the rows are nodes, the columns are nodes, and then there are Boolean values at each cell. I'm thinking Excel and spreadsheets when I say that. But each location is going to have a true or false. True if there's an edge between those 2 nodes, and false otherwise. False if there's no edge between those nodes. We're not going to do that in 116. We're going to use adjacency lists. In my opinion, they're easier to code, easier to work with in your code, and they look a little better on a slide than having a big old matrix. And they're better, more efficient for sparse graphs, which is what we're going to have here for this example and for the homework. They're both going to be pretty sparse graphs. Yeah. Mm-hmm.
Relatively small.
Yes. Yep, exactly. Yeah. Yeah, an adjacency list is much more space efficient when there's very few edges of the possible edges. So there are n squared minus n total possible edges in any graph, where n is the number of nodes. If you're not getting anywhere close to that, which we're not getting anywhere close to that here, then an adjacency list is much more space efficient. And computationally efficient too, because a matrix, you want to find all the neighbor, depending on your algorithms, matrices are more efficient for certain algorithms, but if your algorithm needs to know all the neighbors of a particular node, that's O of n runtime, because you got to go across its whole row or column to be able to find all the neighbors. If your algorithm, which breadth first search does require this, if your algorithm requires finding all the neighbors of a node, adjacency list is going to give us the most optimal way to find that. You just look up a node and find all the neighbors. But I haven't, for those of you not in 199, I haven't introduced adjacency lists yet. So an adjacency list is going to store all of the neighbors of each node. So for each node in this graph, we're going to remember all of its neighbors. So UCLA has neighbors, and when I say neighbor, I mean connected by an edge. UCLA is connected by an edge to Stanford, SRI, UCSB, and RAND. So in the adjacency list, UCLA is going to have neighbors Stanford, SRI, UCSB, and RAND. True for any node. If I pick on SDC, SDC has neighbors Utah and RAND. SDC has neighbors Utah and RAND. And each edge will be in this adjacency list twice. So for example, if SDC has neighbors Utah and RAND, if I go to Utah, I expect to see SDC. If I go to RAND, I expect to see SDC. So each edge is in here twice. So we do get this kind of idea of duplicate data, that we have everything in there twice. The reason for that is because this is an undirected graph, meaning that every edge that I have in this graph can be traveled in either direction. I can go from UCLA to RAND or from RAND to UCLA. That's not always the case. In general, it will be always the case in 116. That won't always be the case in general, and you might have a directed graph where edges can go just one direction from UCLA to RAND, but not from RAND to UCLA. That could be the case, and the adjacency list is well equipped to do that. You just add the entry in one of those, for one of those nodes and not the other one, to indicate that you can't go backwards through that node. It's a one-way street. Or you can only travel in one direction in this graph, or it's a one-way in our game. Going from one grid location to the other, it'd be a one-way that you can't go back. Maybe it's a jump down the cliff in our game or something like that. We're not going to mess with that in 116. But that's something that could happen, and that's why we have duplicate data. For an adjacency matrix, for an undirected graph, the adjacency matrix will always be symmetrical. You always have matching entries for a pair of nodes. Same thing here. You have duplicates in the data. You always have a ×2 increase in space for your undirected graphs, for what it's worth. In the code, it's going to look like this. This is in the examples repo, and in the homework handout, there's a graph class. We're going to remember the nodes as a map of int to the type of the type parameter. And the type parameter is going to be whatever we're storing in this map. And this is a point of confusion, so I want to spend a decent amount of time on this. Where in the example we're going to see in lecture, that type would be string. So we're going to store strings in our graph. So the string UCLA, Stanford, SRI, etc., these are all going to be stored as strings. But when we work with our data, when we do something with the data in a map, we need some way to be able to work with it, and we might not be able to work with strings directly. For example, we want to run breadth first search and find paths through grid locations. That's our ultimate goal. And working with the grid locations directly would be, I was going to say tricky, but not too tricky. But whatever algorithm we write using grid locations can only ever be used for grid locations. We want to write something similar to find routing through the old days of the internet when the nodes are represented by strings. We're going to have to write a whole new algorithm for that. So to avoid this situation, we're going to work with integer IDs only. We assign each node a unique ID as an int, and then only ever work with those integers. So when we add a node, I want to add UCLA to this graph. I'm going to call add node, give it some index. I'll start with 0. I'll give it index 0 and the string UCLA. When I add Stanford, I'm going to give index 1 string of Stanford. And I'm going to give each node a unique ID to make sure that I can identify each node when I need to. That's going to add that node to my nodes list, mapping the ID to the value of that node. And then all my algorithms, I'm just working with IDs, including adding edges. When I want to add an edge between two nodes, I'm going to give it the indices of the two nodes, and then update those two entries in the adjacency list for each one of those nodes. I'm going to add that entry to each one of those nodes' lists. I'm going to add the other node to their list. So I add UCLA as index as ID 0, Stanford as ID 1, and then I'll call add edge 0, 1, and that will say Stanford and UCLA are connected by an edge. And then when we write breadth first search, we write it based on these integer IDs, and it doesn't matter if we're routing through the internet or routing AI through our grid locations. It won't matter because we're going to write it to IDs, and those IDs, and we'll write one algorithm that works with ints, with IDs, and then that can work with a graph of any type. Doesn't matter what our graph is, what type it is. And then once we finally do have the answer we're looking for, then we go back to this nodes map and say, hey, I got all these IDs. What do these actually represent? We go to the nodes and say, look up the value for this ID, look up the value for this ID, look up the value for this ID. So for your homework for the application objective at least, you find the path, which is just going to be a list of integer IDs, which won't make much sense. But then you go back to this nodes map and say, okay, I got this path of IDs. Which grid locations were these actually referring to? And then you get all the grid locations and return that as a path. But your breadth first search and your path finding is going to be in these indices, these index ID values. To use this code, we'll use it like this. We add each node by assigning it a random, I shouldn't say random, but a unique ID. And then add the edges based on those IDs. So this add edge 0, 1 means there's an edge between UCLA and Stanford. This edge 2, 5 means SRI and Utah are connected by an edge. We're going to build our graph manually by adding these nodes and edges to our graph. So creating a new graph, adding every node we want, making sure that we keep the IDs unique. These are IDs are used as the keys in both these maps. So adding a non-unique ID is going to lose us some information. All the information about the node that had that ID is all going to be overwritten when we add that node, because the indices will be the same. So these have to be unique. And then add all the edges based on IDs, and we'll eventually run breadth first search by those IDs. Yeah. I believe it does nothing right now, right? I just left it with a to-do. That used to be a homework objective. You can just delete that whole thing if you want, or fill it in. If you will find is path method useful, you can implement that and then call it. Like is path is useful for like testing the application objective. Call is path. I have this path. I want to know if it's valid, and have that return true or false if it's a valid path. But what is a path? Is good timing. So we have this idea of a path, which is a sequence of nodes that are all where each adjacent pair of nodes in the sequence are connected by an edge. So UCLA, SRI, Utah, MIT, BBN, RAND. UCLA, SRI are connected by an edge. SRI and Utah are connected by an edge. Utah and MIT are connected by an edge. MIT and BBN are connected by an edge. BBN and RAND are connected by an edge. So since they're all connected by an edge, any adjacent pair of nodes are all connected by edges, this is a valid path in this graph. SRI, Utah, BBN. SRI, Utah connected by an edge. Utah, BBN not connected by an edge. This is not a valid path in the graph. So a path is a sequence of nodes all connected by edges where each adjacent pair of nodes is connected by an edge. On Wednesday, we'll also talk about the length of a path, which is the number of edges in a path. So our ultimate goal that we're building up towards is an AI location, or an AI player finds the closest AI player to it, and then finds a path from its grid location to the grid location of that closest player. Finds a path of grid locations from its location to the target location, which are all valid moves, which will be edges in the graph. So any two adjacent grid locations are going to have an edge connecting them, unless one of the two is a wall, or both of them are walls. So we want a valid path of shortest length from that player's location to the closest player's location. It's our ultimate goal. So we want to find a path of minimal length. We won't talk about of minimal length until Wednesday, but that's our goal. So any questions at this point? We did the whole structure of a graph, introduced paths, and I'm about to go into breadth first search. But any questions on any of this so far? Yes? For this class, I'd say yeah. I would count that as a valid path. But our ultimate goal is to find paths. I forget the exact definition. If you can backtrack or not. I believe the definition of a path you can, like the raw mathematical definition. I'll be fine with that in this class. But since our ultimate goal is to find paths of shortest length, that would never be something that you would return on your homework. Yeah. Oh, I thought you had a question. You have a question. All right. Yeah. Mm-hmm.
So is this one?
Yes.
It is? Okay.
Mm-hmm. All right. Any other questions? And we'll only see the non-directional graphs. We won't see any directional graphs in 116. You might in 191, I forget. You probably will in 250, and you definitely will in 331. You'll see those. 116, we don't have to go there. We have a goal. We have a mission. We're going to get to pathfinding for AI. We're going to skip anything that's auxiliary. We're going to go right to that path, learning exactly what we need. All right, no more questions? Do this. Breadth first search. So I'm going to introduce breadth first search today. Wednesday, we're going to go in depth on how to actually do breadth first search. Sounds weird, but how to actually do it in your code. Where today I just want to introduce the idea of this algorithm. So first, let's talk about connected components. So what breadth first search will do for us is attempt to visit every single node in a graph. But it's not super good at doing that. It's actually pretty tricky to visit every node in a graph. I shouldn't say pretty tricky, but there's some extra things we need to think about that we never had to worry about with arrays, linked lists, trees. Key value stores, I guess. I can throw those in there. For the first 3 data structures you've learned, arrays, linked lists, and key value stores, you just throw it in a loop. You have iterators that are going to visit every piece of data. For linked lists, we cracked open how those iterators work. It's by constantly going to the next reference and visiting every node. And then for trees, we had to use our traversals. We had to get a little more creative with it, and we pulled out recursion to be able to visit every node in a tree. Which, by the way, visiting, it's like the simplest thing we can do with the data structure. Let's just visit every single node. So we have to at least get there before we start doing more advanced things like binary search trees with trees. We had to do traversals before we can talk about that. Do something simple first. And then for graphs, let's traverse this before we can talk about, pathfinding. But it's actually hard to visit every single node in the graph, and breadth first search isn't going to do that for us, but it will visit the connected component of whatever node we choose to be the starting node of our algorithm. So with breadth first search, we're going to pick a node for the starting node and visit the connected component of that node, which is all of the nodes that you can reach via a path from the starting node. Now, this graph, no matter what node I pick, I'm going to visit every single node in this graph because this graph is connected, which means there's only one connected component. There's one connected component is the entire graph. Cool, we're done. So our breadth first search is just going to visit every node. That's not necessarily always going to be the case. And warning, I messed up my slide here. I updated the adjacency list, so you can see the edges being removed, but I forgot to remove them visually. Or rather, I did have them removed, but when I redid my slides to dark mode, I forgot to remove them again. So this edge and this edge are no longer supposed to be in the graph. And now when I start at UCLA, I'm only going to visit these nodes because this is the connected component starting at UCLA. If I start at any one of these nodes, again, with this node, with this edge and this edge removed, I'm only going to visit these nodes. And if I start at any one of these nodes, I'll visit all of these nodes, but I'll only visit one of the 2 connected components no matter which node I choose as the starting node. Now you still can visit every node. You would choose a starting node, visit the connected component, and then go back to your graph and say, are there any nodes that I haven't visited? And if there are, choose one of those nodes, visit all the connected component of that node, and then keep doing that until you run out of nodes, until you've visited every single node. So you can still do it, it's just extra bookkeeping, extra work to be done. And for this graph, we can just look at it and we can find our paths. Like, it's not that hard. It's a graph that I'm using for an example. You would never bother writing an algorithm for this graph, right? You would just look at it and be like, oh yeah, there's the shortest path between those 2 nodes. But this graph represents the early days of the internet, and the internet's got a little bit bigger since those days. This is what our internet looks like now, and with this one, you're not just going to look at that and tell me what the connected component is, if there's any, this is links between IP addresses. Does the site at this IP address link to this other IP address? You're not going to look at this and just be like, okay, are these 2 values connected? Is there a dark web component in here that I just can't parse visually? I don't know. I'm going to need my algorithms. I'm going to need breadth first search to be able to navigate this, especially if I'm trying to find the shortest path. What's the fewest number of clicks I need to get from this URL to this URL? I want some algorithms to do this. I want the computer to figure that out for me. I'm definitely not doing that visually. So we need these algorithms when our problems are a bit bigger. And that's where breadth first search, which I'm going to try to pronounce and spell correctly every time. My slides used to say bread first search and breadth first search. I think I got all the typos gone, but I also introduced a new typo this semester with these edges being there, so we'll see if I missed any. So with breadth first search, The idea is to choose a starting node and continuously explore its neighbors of its neighbors, neighbors of its neighbors' neighbors, until you run out of nodes to explore. So we're going to start. I'm going to choose UCLA as the starting node. And I'm going to look in your code. You're not going to have the visual. You'll just have the adjacency list. I'm going to look in my adjacency list for all of its neighbors. And I'm going to visit all of those neighbors. And for all of those neighbors, I'm going to look at all of their neighbors. So Stanford, SRI, UCSB, and Rand. I'm going to look at all of those neighbors and visit all of them. Again, this is the modified graph where this edge and this edge aren't actually there. So I'm going to visit their neighbors and just visit Utah and SDC. And I'm going to keep repeating this process until I go a whole round without adding any new nodes. Once I have no new nodes explored, I know I've explored the entire connected component of my starting node. Which in a nutshell is breadth first search. There are tons of little details like how the hell do you code that that we'll talk about on Wednesday, but really that's breadth first search. That's the concept behind it. It's the idea behind the algorithm. And we never want to visit a node twice. So before, with our traversals, I said we're going to get stuck in infinite recursion immediately. We do have to take care of that with breadth first search. So what we'll do is whenever we're checking the neighbors of a particular node, we're going to only visit the neighbors that have not yet been visited. So when I'm visiting SDC, by the time I get to that point in the algorithm, its neighbors Utah and Rand have both already been visited. So we're just going to skip them. We're going to say those nodes have already been visited, not going back there. So we're going to keep track of which nodes have been visited and which nodes I still have to visit, and then go until we run out of things to do. So getting into a little more detail, we're going to use a queue, or at least the idea of a queue. With queues, since you have this issue of appending and prepending or removing from the front, removing from the back, you have that decision. It can be easier just to use Scala's built-in queue and then use enqueue and dequeue for this specific application. Never true with a stack, but for queues, since you have that issue where you have to work on both ends of it, can be easier just to use the built-in queue of whatever language you're using. Obviously Scala this semester, but use a queue to keep track of which nodes to visit. This will maintain the order in which you visit the nodes, which will be very important with pathfinding. You need to visit the nodes in a specific order. If you use a queue, that order is already set for you in this first in, first out data structure. In queue, the starting node, wherever you want to start. For your homework, this is going to be the location of the player that's deciding where to move. When you visit a node, you're going to dequeue off of the queue to visit that node's neighbors as long as they haven't already been visited. And any neighbor that hasn't been visited, enqueue them. Repeat until the queue's empty. If the queue's empty, that means there's nothing else to explore. You've explored the entire connected component of the starting node. So that's a little more detailed view on breadth first search. If you want to know if two nodes are connected, if there exists a path between nodes A and node B, choose either node A or node B as the starting location of breadth first search, run breadth first search, and then if the other node was explored during the process, you know that those two nodes are connected. Let's shift gears. Any questions on any of that? I'm going to shift gears to some IntelliJ. So I have the example from lecture. I'm going to create a bunch of nodes, create a bunch of edges. Then I added a print line just so I have a spot to put a breakpoint. For some reason, you can't put breakpoints on blank lines. I kind of want that functionality, but whatever, we don't have it. So I added a print line just so I could set a breakpoint. We're going to run this in the debugger. So when we add these nodes and all these edges, I want to show you what's stored in those two maps representing our graph. So we have our graph, we have our nodes, which are going to map those integer IDs to the actual value of the node, depending on the type of the graph, which is a graph of strings. The ID 5 was assigned Utah, or we assigned it to Utah. 10 is Carnegie. 1 is Stanford. And just a reminder, there's no order to key value pairs. The order is irrelevant to us. It is relevant to the computer. It's actually ordered by the hash value. This is built on a hash map, so it's ordered by the values of the key, the hashes of the values of the keys, is how it's stored here. That's a topic for 250 hash maps, which they just learned last week in 250. So around this time next semester, you'll be like, oh man, I wish I didn't know how hash maps work. This is confusing. And then 9 to Lincoln, etc. Hash maps are fun. I shouldn't say it like that, but they do get a little confusing, just as a heads up. Maybe not, I don't know. Not too confusing. Depends how you handle collisions, that can get confusing. So the node 0, the one that I really want to point out here, the adjacency list is going to have keys for each node, and then the values will be a list of all of its neighbors. This is always as integers, and this is always a point of confusion. We have a map of int to list of ints. It's probably I believe the most complex data structure that we see this semester, since we have this nested data structure. We have lists being the values of a map. Gets a little tricky. But we have the keys of the node, so node 0, which is Stanford, or UCLA, Stanford's 1, and neighbors of 1, 2, 3, and 4 in that list of ints. So this is saying which neighbors, the node with ID 0 is neighbors with the node with ID 1, 2, 3, and 4. The node with ID 5 as the key in this map has neighbors 2, 6, and 7, and so on for each one of these values. So that's our adjacency list. It works off the indices, those IDs. I'm using IDs and indices interchangeably in this example when I'm talking about graphs, but the IDs represent them, or the indices for each ID, each node. Based on those integer IDs, we're storing the information for all the edges in the graph. Any questions on this? We're feeling all right. For those of you in 191, I think a lot of today was review, but I don't believe you've done breadth first search, so that should be new. But then again, neither did I with any justice today. So Wednesday we'll really get into that. All right, we can get out of here a little early today. Fine with that. Have a great day. I'll see you all Wednesday when we'll talk about pathfinding with breadth first search.